So good afternoon to all. Today I have the pleasure to host here and to introduce Dr. Carlos Varela, who is a professor in computer science and founding director of the Worldwide Computing Lab at the Helesala Polytechnic Institute. He has his undergraduate and his master's and bachelor's at PhD in organic campaign in computer science. He's author of a book called entitled Program Distributed Computing Systems Foundational Approach, published in MIT Press. And he's associate editor of the ACM computing surveys, the IEEE Transaction of Cloud Computing, and the IEEE Internet of Things Journal. Dr. Varela is also an instrument-rated pilot with over 1,100 hours of flight experience. And his current research interest, of course, is safe flight, of course, software verification, cloud computing, middleware for adaptive distributed systems, and concurrent programming models and languages. And today he will give us a presentation about verification and formal verification in cyber physical systems, which is a very hard topic because, as you know, things are distributed and the real world is also very hard to control. So please, the floor is yours.
Thank you, Professor Endler, Professor Alves, for hosting my talk. Thank you, everybody, for coming. And for those who are online, thanks for participating. I'm gonna assume that I have about 50 minutes. So we started a little bit late, so I'm gonna try to stay within 50 minutes. Is that okay?
30 minutes.
30 minutes. Oops. So I have a lot of information. I can skip a lot of slides too. But I will try to leave time for questions and answers, but if there are any questions during the presentation, I'll be happy to take them. So the talk will have a background on why do we want to have formal verification in cyber-physical distributed systems. I will talk a little bit then about verifying concurrent programming systems using the actor model, actor system verification. This is some work that shows kind of the way forward in terms of formal verification for concurrent software. Then I will talk about verification of distributed cyber-physical systems. So the challenge, of course, with cyber-physical systems is that, as Professor Endler mentioned, there is a lot of stochastics, there is a lot of uncertainty. It's hard to bring the field of formal verification into that world. But we'll take an example which is coming from aerospace. We're trying to, in particular, do decentralized coordination between multiple flying vehicles, between multiple planes and drones. We want to avoid collisions, and we want to do that in a way that they do it in a coordinated fashion. And we want to verify formally that they actually do what they are supposed to do. So the first part of that section of the talk is going to be on proving that the flight plan that a plane produces doesn't have any conflicts with the existing air traffic. That's the first part. My plan doesn't conflict with anybody else's plan. The second part is, now I have a plan, I propose it to a group of aircraft in some airspace. So that requires consensus, that requires everybody to agree on my plan so that I can join the airspace. There will be multiple candidates, and only one of them should be able to enter, because there may be conflicts if multiple candidates get accepted at the same time. So you need to accept essentially only one at a time, and that requires this consensus. So we look at consensus, safety, and progress. And finally, once we reach consensus and we have a new aircraft in some airspace, then we talk about distributing, propagating that knowledge. So letting every other plane know that there is a new plane in the airspace. So that requires knowledge propagation, and we're talking about those three as a motivation of a decentralized coordination algorithm for air traffic management. Then we got at the end of the talk into data-driven models. A lot of the models we build are based on data, and we need to verify that the models predict things correctly in the future. But models which are based on data sometimes make mistakes. So the question is, how can we bound the input space of these models, what we call envelopes, so that within those envelopes we can still guarantee some properties? And we do that both for safety and for progress. So that's the main outline of my talk. The motivation for the talk, and I don't know if this is gonna start here, but the motivation for a lot of the work I've been doing has to do with existing aircraft accidents that have occurred. These two accidents that are in the images, and also the third one in the bullets, are accidents that happen because the plane stalled. They happen because the angle of attack of the aircraft went above a critical angle, and then essentially the lift at that point doesn't happen anymore. The airflow becomes disconnected, and there is an aerodynamic stall where the wings stop producing lift. And in these cases, one of the problems is that the pilots or the autopilot did not realize that the plane was in a stall or did not detect it appropriately. For example, in the Air France 447 case, the right seat pilot had nose-up controls, thinking that the plane was in this normal mode where the plane keeps, in the fly-by-wire system, the plane keeps a safety margin, and even if you put nose-up controls, the plane usually does not let you get into a stall condition. But because there was wrong data, the pitot tubes had ice and the airspeed was incorrect, the plane had moved from a normal mode to an alternate mode. In the alternate mode, the pilots can do anything, including stalling the aircraft. The right seat pilot had the nose-up controls, thinking maybe that he was covered by the fly-by-wire system. In reality, the plane was stalled, and when the captain that was sleeping in the back came forward to the cockpit and realized that the plane was in a stall, the plane was already 1,000 feet, maybe 300 meters above the ocean, going 10,000 feet per minute. So it was already too late. So these stalls not being detected are a problem, either because the pitot tubes ice or for other reasons. But then we also have false positives, where actually the plane thinks it is in a stall, but it is not. The Boeing 737 MAX 8 accidents happened because the angle of attack indicator was saying that the plane was in a 50-60 degree angle of attack. The automated system says, we're going to stall, it is dangerous, so I want to put the nose down. In reality, the angle of attack was incorrect, the plane was straight and level, and the nose down controls send the plane to the ground. So this is a case where the system detects a stall when the plane is really not in a stall condition. The pilots tried to move the nose up, but the MCAS system was insisting in moving the nose down controls, and that caused the grounding of the Boeing 737 MAX 8 aircraft. So we have far too few sensors in our current aircraft. We need many, many more sensors to be able to understand what the state of the system is. We need to be able to tolerate, withstand individual sensor failures, and have the ability to understand the state of the aircraft from that sensor network. But that is not so easy. That requires a lot of research. One of the projects that is funded by the Air Force Office of Scientific Research with my colleague, Professor Kopsatopoulos in the Aerospace Department at RPI, is trying to create a smart wing. So it's a wing that has a skin covered by sensors, and these sensors produce data. And the question is, given that data, can we say, is the aircraft in a stall condition, or is the aircraft in flutter conditions, or what is the actual state of the aircraft given those values? This is a data-driven model, and the question is, how do you, from that data, formally verify that the system is actually going to estimate the state correctly? So it's a challenging problem. Typically, we're going to have multimodal sensors, so we're going to have piezoelectric sensors measuring energy. We're going to have different types of sensors covering the skin, and the question is, how do we analyze all that data coming from all those sensors? Some of them may be failing to be able to estimate the state properly, and how do we bring formal verification into the picture here? So that's one of the contexts for this work. Other accidents have also occurred because of collisions. So there have been, even though air transportation is still by far the safest mode of transportation, there are collisions, there are errors that happen typically because of human errors. In one of these cases, the human was telling the pilots to go down, while the TCAS, the traffic collision avoidance system in the plane, was telling it to go up. So the pilots were receiving contradictory advices, and they followed the human advice and they crashed. So there have been a number of other occurrences where the air traffic controller confuses one plane for another and asks it to go and do a 360-degree turn. Some other plane in the airspace is doing the 360-degree turn, not knowing even why, while the plane that had to do the 360-degree turn goes and crashes against another. So as the airspace becomes more congested, as we move into advanced air mobility scenarios like urban air mobility, when we have drones that are flying Pixas and Ubercopters, and as the airspace becomes more congested, of course we need more autonomous kind of airspace management where planes can actually, in a decentralized way, coordinate and take decisions. And that essentially is the focus of the second funded project by the National Science Foundation, which is with Professor Stacy Patterson in the Computer Science Department, where we look at the Internet of Planes as a model for communication between aircraft, both for coordination and also for situational awareness. In the case of the Air France 447 accident, turns out that the radar on board the aircraft saw a small cell and it didn't see the bigger cell behind. The smaller cell occluded the bigger cell. This is as if you are hiking and the small mountain doesn't let you see the bigger mountain behind. And that's why in the first place the pitotube's iced. That's why the plane did deviate, but not enough to avoid the bigger thunderstorm cell. And the question is, can we have the plane behind it tell the plane that there is bad weather coming? So how do we have the situational awareness that can arise from extended sensing ranges by having communication between aircraft? So we have done a number of works here where we analyze sensor data, we try to detect failures in sensors, we use this notion of error signatures, and then we give advice to pilots. And the question is, can we have automated notification, for example, to nearby aircraft? In the previous example, in the case of the Hudson, if the pilots had gone directly back to LaGuardia after the engine failures, they could have landed at LaGuardia. But by the time that the controllers, the tower controllers came back and said, you can land in LaGuardia, it took 45 seconds. Too late. You know, they were able to come back up to 29 seconds. So if they had turned back to LaGuardia 29 seconds after the birds impacted the engines, they would still have been able to make it. But because of the time it takes for humans to communicate and let other traffic know, when the controllers told the pilot, Sullenberger, you can come back to LaGuardia, he said, no, I cannot, I'm going into the river. With an Internet of Planes kind of scenario, of course, we can notify other aircraft nearby in the case of emergencies, and this happens in milliseconds, not in human time, but in computer time, which is what you want in this kind of emergency scenarios. So that's the motivation for the work that I'm presenting. Formal verification, of course, is very challenging and hardly used, except for safety critical applications. It's likely 1 or 2 orders of magnitude harder to develop software that is formally verified in hardware than it is otherwise. And that means that it's not something that is easy to do. And one question that we have is, can we use libraries of reasoning so that we bring down that development cost? And this is similar to programming. When you write a program that uses a graphical user interface library, you don't have to think of the lower level pixels and so on, but you can think of widgets and menu items. You can think at a higher level. And that's how we deal with complex systems. We deal with complex systems by essentially stepping on different layers of abstraction and using those libraries so we can tackle that complexity. So what we are proposing to do in our work is to create libraries for reasoning, libraries for formal verification, so that when we want to think at the level of an application, we can use, for example, the theorems for a data structure or for an underlying algorithm, and then prove properties of the application directly leveraging this work. So that's what we advocate for. Most of the formal verification work now uses automated theorem-proving or model checking, which are kind of push-button solutions where people don't have to think too much. We don't advocate for that. We don't think that scales. We don't think that allows us to deal with the complexity required. We advocate for a principled approach where you build these reasoning libraries from the bottom up and you step on those giants' shoulders to be able to prove more complex properties. Of course, the field of formal verification in the last couple of decades has really exploded. Verifying a compiler was a grand challenge for decades, and now we have already verifying compilers. So it is really a good time to be in this field. Lots of tools, proof assistance. There is a lot of things, more papers. In traditional conferences, it's not rare now to see formally verified proofs. So it's a good time to be in this area. But of course, the systems we are dealing with are more and more challenging. We're dealing now with neural network systems that are data-driven, and we need to formally verify them. And it's extremely challenging because sometimes there is not even a ground truth that we can verify against. Similarly, in the case of cyber-physical distributed systems, there are stochastics, there are wind gusts, there is turbulence, there is structural damage. There are so many things that make it very hard to formally verify a piece of software. So we don't need normal methods. As I am going to propose, we are working on this notion of safety envelopes and progress envelopes to prove probabilistic properties, which I think is the best we can do. We cannot prove a compiler is relatively much easier to verify because there is a source language with a well-defined semantics, there's a target language with a well-defined semantics, and there's a translation function, much easier, deterministic. In the case of a plane, the behavior is completely stochastic, and the best you can really do is probabilistic. So let me talk about, let me see my time, how we're doing, and what I need to skip. Let me start by looking at concurrency. Proving concurrent programs correct is harder than proving sequential programs correct. We use a model of concurrent computation called actors. In actors, and by the way, Carl Hewitt, who was the creator of the model, he passed away this year. He was involved with Jean-Pierre Briot. And he was the advisor of Gulaga, who was another prime contributor to the actor model, who was my advisor. So it's my grandfather and my father, academically speaking. So an actor essentially is, you can think of it as a unit of encapsulation for state, which is the same as an object, with some clearly defined interface to access that encapsulated state. And then you also encapsulate a thread of execution. So it's a unit of concurrency as well. That means that you cannot have two threads changing the state incorrectly. You can only reply to messages which are sent asynchronously. So an actor is always processing one message at a time, and then there is less conflict. There is less potential for race conditions and so on. So it's a very clean model for concurrency. Unfortunately, it's not the most popular one. The most popular model is shared memory with threads, which is full of problems, but this is a model that is relatively clean and is the one that we may advocate for. And in response to a message, an actor can either modify its internal state, it can create new actors, or it can, let's see. So it's taking some time for this to reboot. Yeah. I might just have to wait.
Here it's
working. Yeah, maybe the connection. Let's see.
We check the cable.
Yeah, it's.
Is the Mac away?
No, it's the laptop. It's this. Is processed at a time, and that prevents a lot of race conditions. Deadlocks are also less likely to happen because, of course, the unit of execution is a full message, and deadlocks may happen at the application level, but are less likely to happen as in the case of threads. And then usually it's live locks what happens. One advantage of the actor model is also migration. If we want to migrate an actor to another runtime, to another computer, to another node, all we need to do is we need to serialize the state, serialize the mailbox, and restart a new thread of execution in the new location. And because messages are asynchronous, there is and the state is encapsulated, there is no problem. So adapting systems by migration with actors is much easier than with other approaches. You still need to have a way to reference the actors as they migrate, so that requires a universal naming mechanism, which is something I did during my PhD thesis back in 2001. And one thing that the actor model also has is fairness. The idea being that when a transition is infinitely often enabled, it must eventually happen. Fairness turns out to be very important to prove progress. And progress is quite important in, for example, the context of planes, trying to coordinate. You need to make sure the consensus will actually move forward. So I'm going to skip a lot of the details in the interest of time. We advocate, as I said, for libraries. Just like programming, we advocate for libraries of reasoning, where we have proofs at different levels and where we reuse proofs as much as possible, where we try to understand the application level properties as best as possible and do theorems rather than just model checking. So, sorry, this jumped on me. So, for example, in the case of actors, we might have theories that talk about binary relations, transitive, reflexive properties. We can essentially build up to a transitive closure. We can talk about transition paths. So the way we model concurrency is as if we were taking a picture of the system where we have the different actors and the messages in transit. And then we talk about, that's called an actor configuration. And then we talk about computation as a transition between actor configurations. It's a labeled transition. So a label maybe received a message or created a new actor. And what we do then is we can essentially reason about these configurations of actors. We can say, for example, being at configuration T0 and then receiving a ticker from the ticker by the clock will move me into configuration 1. So essentially, we talked about computation sequences as labeled transitions between configurations, and then computation trees when there are non-deterministic choices. If I can choose this message or that message, that's going to lead me to different distributed states. So that's how we reason about computations. And we can, for example, in the case of the ticker, this is a typical example where you have a time in a ticker with a time 00011 here, and you have a clock. Sorry, excuse me. You have a clock with a time 00011 here, and then you have a ticker. The ticker has some internal states. When it is in state 1, it sends itself a continue message. When it is in state 2, it sends a tick to the clock, and then the clock, when it receives a tick, it can consume the tick and update its state to 1. And then the clock, when it is in state 3, it comes back to state 1. So you can see that this can go on forever because this is similar to this one, except the time has increased by 1. Now, what could go wrong is that here there are 2 messages that can be received. And if you have an unfair scheduling mechanism, you could have a scheduling mechanism where the continue gets processed, but the ticks keep accumulating in the network, and the ticks never get received. So the clock would never increase its time. Because of fairness, that cannot happen. So fairness is a critical assumption, a critical axiom to prove progress, even in some very simple system like a clock and a ticker. We prove that. The proofs here are typically proofs by induction, where we say if some property is true in the initial configuration of factors, and we assume it is true in T and can take any step where the step is the label of the transition, then it's going to be true for all computations from that sequence. So we can prove a property for all possible computations from a given initial point, typically by using structural induction on the configurations. So this is some way to define the behavior of the clock system, and this is the axiom that says that if a message, if a transition is infinitely often enabled, in particular here, if there is a receive that can happen, and that can happen infinitely often, then either it happens or it becomes disabled. So this essentially says, when a transition is infinitely often enabled, it must happen. And this is the fairness axiom that we need to be able to prove guaranteed message delivery and to be able to prove properties like unbounded non-determinism, which means that the actor can reach an arbitrarily large time in this example. So here, for example, we say for all t, the clock can reach a state u that is greater than or equal to t. So essentially, it doesn't matter how big a number you give me, I can show that the clock will reach that number. This is unbounded, and it is non-determinism because, of course, we don't know if we ask the time, we don't know what time we're going to get, but we can get a time that is arbitrarily large. So this unbounded non-determinism was a property that Carl Hewitt said that distinguished actors from Turing machines. So that gets a little bit philosophical, depends on what kind of Turing machine you use, but unbounded non-determinism is an important property, and fairness allows us to prove progress, where other models like the pi calculus that don't have fairness will not allow us to prove progress, because it could be that the transition that always goes into the Cs and never picks up a tick, that transition is valid. So then the clock would stay at time 0 forever. So fairness is quite critical. And the idea here is that as we move from sequential to concurrent systems, we have to deal with more properties. It's more complex. As we move from concurrency to distributed systems, there may be partial failures. And now we need to deal with scenarios where part of the system is working and part of it is not working anymore. When we go to mobility, then we need to deal with heterogeneity in latencies. We need to deal with potential partial failures again during migration. So as you go from mobile to adaptive and intelligent systems, the point is things become more complex. And I think the need for formal verification, in a sense, becomes more manifest. We need to know what's going on. We need to know how to prove formally that a property actually holds. So that's, again, why we advocate the approach of formal verification, while model checking, for example, might work for small systems. As you increase the complexity, these approaches just, or automated theorem-proving, these approaches simply fail. I think you really need to go and do it manually in a way that is human understandable. So that's concurrency. Of course, all distributed systems are concurrent. And now when you add the cyber-physical component, things become more difficult and more exciting. And as I said here, we have three main parts. One is conflict-aware flight planning. And here the idea is we're going to look into these urban air mobility scenarios. We think that the current ATM system, as safe as it is, still is prone to human errors, and there have been accidents, doesn't scale too well, and cannot be verified for correct. So we advocate for an autonomous air traffic management system that actually can be proven correct under some conditions, of course, but be clear about those conditions. So the problem here is that we have a set of owners of some airspace. Let's suppose these three planes currently own the airspace. And let's say we have two candidates that want to enter this airspace. So essentially, what we want to advocate for is that each of these candidates is going to propose a plan. It's going to say, look, this is my plan, and here is a proof, here is a theorem that shows it doesn't conflict with any other plan. Of course, each of these candidates may have its own theorem and its own proof, but the two of them may conflict with each other. So here's where you need to accept the candidates one by one. How do you accept one and reject the other? Well, that's where you might have to do something like consensus, where the planes in the current airspace decide which of the two planes they accept, and once they decide on which one they accept, then they can admit it. So there are essentially two stages. One where the owners agree on a single candidate's flight plan, again, coming with a proof that it doesn't conflict with the current flight plans. And then the stage two is propagating that knowledge so that everybody has the same distributed state. And the coordination algorithms that are required are consensus and knowledge propagation. So consensus allows us to agree on a value, and knowledge propagation to propagate that new value to all the elements, where the value is a set of flight plans with the new candidate accepted. So the question here is, how do we compute a conflict-free flight plan? And what we have is a flight plan is a series of waypoints. So we have a three-dimensional space and time, and we assume that there is a constant velocity in between points. And what we're going to do, which is very similar to what's done in the real world now, is if there is a potential conflict, the traffic controllers will tell this plane, for example, to slow down. So this plane is going to have to go slower so that it gives time for the others to come, and that way it can pass. So that's what we're going to do in the algorithm. In the algorithm, we're going to guarantee that there are no near mid-air collisions. And near mid-air collisions is when two well-clear volumes intersect. So essentially, the airspace usually has 500-foot separations in the US. So 500-foot separations means that there may be traffic going one way at this altitude, 3,000 feet, and then there will be another plane going at 2,500 feet or 3,500 feet. So essentially, 500 foot separate the traffic, and that's typically the height that you use for these well-clear volumes. And then D, of course, it depends on the airspace, but the idea is to avoid these near mid-air collisions. So that's what we do. We start with a set of traffic flight plans with some well-clear volume parameters, and then we start with a plan that might have a conflict. It may not be safe. There may be a near mid-air collision. So what we do is we're going to recompute the speeds of the different segments with some set of allowed ground speeds to find a plan that is safe. That's the strategy that we do. So we essentially do not change the three-dimensional spatial shape of the plan. We only change the time by adjusting the airspeed. That's what we do. And that has the advantage of not having to deal with potential collisions with mountains or towers. Or if you respect the original 3D plan, then you keep out of obstacles. So say that you can do 120, 100, or 80 knots. So what we do is some very simple algorithm again here to find an assignment of speeds that doesn't produce conflicts. And if some assignment does produce conflict, then we try the next. And we keep trying until eventually we have an assignment that works. And what we do is we prove formally that this assignment is safe and that the algorithm is complete, meaning that if there is an assignment, it is found. So that's the safety and completeness proofs, and they are done in Athena, which is a deduction language. It's a language where you can put the axioms and put the assumptions, and then you can actually prove the theorems. But this is a human writing the proof. So a human has to specify all the elements, and what the system does is to check that all the steps are well justified. So Athena has a computation part and a deduction part. The computation part is like any functional programming language. It has procedures that can produce values or can have an exception and exit. There may be an error, or they may halt and stay there forever. And then the deduction, analogous to a procedure, is called a method. A method, when it succeeds, it produces a theorem. And the guarantee that the language gives you is that the theorem is a logical consequence of the axioms. It's sound. That's the guarantee. So very often when we're writing these proofs in Athena, we try it out and the system says, no, that step is not correct. So you need to figure out either add a new axiom, or maybe the theorem was actually not true. So you need to reevaluate. And when you do get a theorem, that means that it is a logical consequence of the axiom. So this proof assistants are very, very useful in giving you assurance that the theorem really, really holds, as opposed to informal proofs that may be written in a paper that may have holes and you don't even know about. So that's the case of creating the plan. And so far, it's all deterministic. So far, so good. So far, it's actually relatively easy. And what the system looks like, it's the interface is not that great. It's just a program that you give it a file with all your theorems, with all the deductions, and then it just produces the theorems and quit. So the interface is nothing fancy, but again, it gives you a logical soundness guarantee, which is quite important. So now let's look at consensus. Consensus requires safety and progress. Safety means that that only one value is agreed upon, and progress means that actually eventually some value gets agreed upon, so it doesn't stall. Obviously, in decentralized admission control, we want to be able to have multiple proposers. Many of the algorithms that do consensus require a leader or a single proposer, and that makes them really not suitable for what we want to do. What we want to do requires, in some airspace, planes are coming and going, and you want to really have this decentralization. So we wanted something with multiple proposers, and you still want to make sure that you guarantee progress, because progress becomes compromised when you don't have a leader. It's harder. So what we do is we take the CNOT part of the Paxos algorithm. The one that is very well known is called Paxos, but Paxos in a sense assumes a leader. So we take only the CNOT part, which is the one that doesn't assume a leader and requires and allows for multiple proposals. And we separate the edges into proposals and acceptors. And the idea is that consensus is reached when a value is approved by a quorum. A quorum typically requires, typically it's a majority of the agents in the system. And for the algorithm to be safe, these quorums essentially have to have intersecting agents. So they must have an intersecting agent. So the idea is we want to verify that the protocol is safe and that it makes progress. And this is an example of a trivial run of the protocol where we have two proposers and three acceptors. And let's say that the proposer A proposes value 5, while proposer B proposes value 2. Now, the algorithm from the perspective of the acceptors is that they will take the higher value. So in this case, acceptor B received both 5 and 2. So acceptor B in this case will promise 5 and will not promise 2. Since acceptor B is in two quorums, let's say that one quorum is AB and the other quorum is BC, let's suppose, then proposer B didn't receive a promise from acceptor B. So proposer B didn't receive a promise from a quorum, so it has to hold. And proposer A, on the other hand, received a promise, so it sends a, sorry, let's see if this shows the other part of the protocol. Maybe my slide doesn't like the, oh. Something froze. Hopefully, let's see. This is not good. Let's see. Let me see if. Okay, now it seems that it's working. I don't know what stopped working, but something stopped working. Okay, so there is the phase 1 where the proposers send proposed values. This is the promise phase. And now this is the accept phase. In the accept phase, proposer A sends the fact that a quorum has accepted value 5. Now, here is where there may be live log. Here there may be live log because in the meantime, acceptor B may have received another proposal with a value 7. Now, when it receives a proposal with value 7, it says 7 is larger than 5. I can no longer vote 5. And then essentially it comes back to phase 1. But if you keep proposing higher and higher values, then the algorithm is essentially in a live log and it never makes progress. So it is challenging to prove progress because of that potential live log. In this case, let's assume that they did not accept promises from higher numbered proposals, and then in that case they accept, and we have a consensus on value 5, and proposer A won the election. This is an example of progress and why it is challenging. Now, there are impossibility proofs. Fisher, Lynch, and Patterson prove that if you have an asynchronous communication model, even if it is reliable, even if messages are guaranteed to get there, a single agent failure can stop any protocol from making progress. So there are already impossibility proofs. You know, if you have a single agent failing in the right moment, you cannot reach consensus. So that requires some strong assumptions. We didn't want to go in the direction of synchronous communication because that's not realistic in a distributed setting. So we needed to have something a little bit less requiring, and we ended up creating a condition that essentially proposers cannot permanently fail. That quorum, there is a quorum of acceptors always available, and that messages for a proposal cannot be interrupted by messages with higher number of proposals. So essentially, we had to put some very strong assumptions to be able to prove eventual progress. And those conditions we formalized, and we proved that under those conditions, effectively, we can get progress. Now, for that, what we did is we modified the actor model, the original actor model. Aga, Mason, Smith, and Talcott already had a language called by value lambda calculus extended with actor primitives. But it didn't model anything about failures. It didn't talk about failures at all. So what we did is we took that model and we created a variant of the model that we call a failure-aware actor model. And in this failure-aware actor model, we essentially allow for actors to fail. And when an actor fails, it cannot send or receive messages or participate in the computation. Now, as we can model failures, we can reason about what's required to guarantee progress. And the other thing that we did is we created a notion of predicate fairness. And predicate fairness essentially means that if a predicate, not a transition, but a predicate, is infinitely often enabled, then it must eventually happen. So it's a different notion of fairness that we also introduced. And under those conditions, we were able to essentially prove that consensus makes progress. This was published in the NASA Formal Methods Conference in 2021, if people want to look at the paper. So let me move on. So essentially, I think we created some, I don't want to say a minimum set, but a pretty reasonable set of conditions to guarantee progress. And I think this is the first machine check proof of eventual progress in CMAT. So again, this is a nice paper for people who want to take a look at it. Now, it doesn't provide time bounds, so the guarantees of eventual progress, it will eventually happen, but it doesn't say when. So it's still limited for the application of avionics, and we work on that later. And it doesn't model any kind of Byzantine or adversarial behavior. So it assumes that agents will actually follow the protocol when they are alive. Once you have adversarial kind of action, things become much harder. So now the next step and the final step is to propagate that knowledge. And the idea is that you want to make sure that every agent, every plane in the airspace knows about the new agent. So essentially the membership has to be known for safety. And notice that in consensus, you can create consensus only with a majority. Here you need everyone. So you actually put even stronger requirements to guarantee that the knowledge gets propagated. No single agent can actually fail. Otherwise, you cannot reach this E2 knowledge that I'm going to explain it. But essentially, in knowledge, you can know a fact, like it is raining, or you can also know that somebody knows. So this kind of knowing that somebody knows is quite important in this kind of context, because you want to make sure that not only you know about all the other planes, you want to know that every other plane also knows about every other plane. That's quite important for safety again. So essentially, the state of knowledge that we want to achieve is called EG2 phi, where phi is the latest set of authorized plans. EG phi is all owners know about the latest set of plans, And then EG2 phi is every owner knows that all owners know about the set of phi. So that's the state of knowledge we need to reach. We created a protocol that is very simple, two-phase kind of a knowledge protocol, and we prove it correct. Again, for proving correctness of this, we needed to assume no failures. Single agent failure, and you cannot prove that everybody knows. So we prove safety, we prove eventual progress, and it has some strong assumptions like at least one propagator does not permanently fail, and no learner permanently fails. So pretty strong requirements. All right, so that leads me to the last part, and I'm gonna have to really go very quickly over it. I'm gonna give the main idea so there's time for questions. But the idea here is once we have models which are built with data, it's gonna be much harder to have proofs. In fact, we're gonna have to move into probabilistic properties. So once you have stochastic behavior, you know, there may be wind gusts, there may be turbulence, there may be damage in the structure of the wing, or these are examples of things that essentially require a probabilistic approach. So what we're trying to do is to create again a reasoning framework that can inform the higher layers of what properties can be guaranteed at runtime. Now, these properties will be probabilistic and they will be parameterized. That means that they will have some assumptions. For example, they may assume that the communication latency follows a Gaussian distribution with some mean and some variance. Under that assumption, then consensus will take this amount of time. So this assumption may not actually be true at runtime. So we need this notion of runtime sentinels, runtime verification, runtime monitors. We need a piece of software that is actually measuring and evaluating whether the preconditions of the theorem are holding or not. When the preconditions do not hold, if you have a new probability distribution, for example, modeling latency, you can actually reproduce the theorem with new values, and you get a new property. That new property may or may not be good enough for the application. But that's the general idea. General idea is we have some proofs, we have some runtime sentinels, they are monitoring the system, and they may notify the operator when some properties may no longer be true. We are actually, with Photiscope Sartopoulos in aerospace, we are building this wing that has some piezoelectric sensors, and we're actually understanding the energy, that the signal energy for these sensors under different configurations. So we put this wing in a wind tunnel with different angles of attack and different airspeeds, and we measure the data. And we capture that data, we essentially take it as probability distributions, and then we create a model. Now, in some conditions, for example, here when the airspeed is 8 meters per second and the angle of attack increases, this is the critical angle of attack here, between 11 and 12 degrees, we can see this giant jump. So we can create a model for 8 meters per second. We create a model easily that can discriminate between a no stall condition and a stall condition. This one, very clean and very nice and very simple. Now, of course, this is only one configuration of airspeed. Once you try some other airspeeds, things start getting less clear. So here, for example, if you get an energy signal that is in here, then it's no longer clear whether you are in a stall or in a no stall condition. And the question is, as a pilot, I am a pilot, we train not to stall the plane so that it doesn't spin. When a plane spins, it's very, very hard to recover. But a plane will not spin if it doesn't stall first. So as pilots, we train to prevent stalls, and if we never get into a stall, we don't get into a spin. Well, the idea here is similar. The idea here is if we have a very clear envelope where we can tell that the plane is going to be in this stall, we essentially keep well clear of that boundary. So if we can keep the control system well clear of that boundary, then we can guarantee safety. That's the approach that we are taking here. So you don't want to be here. If it is somewhere in here where you don't know, you just don't want to be there. You want to be closer. So essentially, this is the intuition behind this, and how this can be useful in a real system. Now, this is what you see when you have all speeds. And of course, when you have all speeds, there will be signal energies that are consistent with stall under some airspeeds. and that are not consistent with stall under some other airspeed. So things become much harder once you add enough data, and I guess probably you know very well how large data can make it very difficult. I was talking to Professor Alves about 15,000 Linux configurations and you know the data you get from that. So this is very simple in that it gets really hard to prove things about it. So what we're gonna do is essentially to say with a very large probability, we can tell that this configuration corresponds to a no-stall or that it corresponds to a stall condition. And that's what we call safety envelopes. So there are two key things. One is the signal that we're getting predictable? Now, does it mean, is it something that we think makes sense? Or is it some value that we never got in the data when we created the model? So if it is some value that we never got, it's likely a sensor failure, for example. So that's the first thing, is the data something that is predictable? And then the second thing is, given the data and assuming it is correct, how much confidence do we give to the classification of stall or no stall? And those are the two key things to determine the safety envelopes. We have parameters. C predictability means that the value is within a probability distribution, within a Gaussian probability distribution, within a C-score. So how many standard variations from the mean, is it there or not? And C essentially, we can tune, and the larger the C, the more values we accept. The smaller the C, the less values we accept. Again, this is going to depend on the application. So the safety envelopes are essentially fluid. You can make the safety envelope very large, but then the property is very weak. Or you can make the safety envelopes very small, but then you have a stronger property. And this is, again, all system design. So we have C predictability, and you can see, for example, that as we increase C, we are going to accept many more values. And of course, once we make C too large, then we're going to accept pretty much all the values. So choosing the right C is one of the key things. And the other part is tau confidence. So tau confidence tells us how certain are we about our classification. And this is essentially a conditional probability. Again, how likely it is that we are in a stall or in a no-stall condition, given some value of airspeed and given some value of energy in the case of the wing. So essentially, what we do here is we create the intersection of C confidence and tau, of C predictability and tau confidence. So for example, given some value of C, we say these are predictable values, but this is never seen in the data. So this would be unpredictable. So this should not belong to the safety envelope. And now here is the conditional probability. This one says, under this data, we know for sure it is a stall. Under this data, we know for sure it is not a stall. But here in the middle, we don't know for sure. So essentially, we take the intersection of those two, and that becomes our safety envelope. The intersection of C predictability and tau confidence is what we call a safety envelope. And the idea again is that when we receive an actual signal energy from the wing, we're going to monitor it, and we're going to say whether it is or not within our safety envelope. And if it is not within the safety envelope, we're going to essentially send a signal saying we don't know for sure whether our classification of stall or no stall is accurate. That's the main idea here. So this is changing. I think this is changing as we change Z and tau. The safety envelopes, of course, change as well. So again, the decision of which Z and which tau to use is critical for safety. But given us a fixed Z and a fixed tau, we actually have proofs. So we have proofs that tell us minimum conditional probability of classification and how far from the mean the values are. So we essentially have some formal properties, even though probabilistic, about the state estimation using the safety envelopes. So this is an example that illustrates increasing the angle of attack. The angle of attack, remember, is the angle that the wing has against the airflow. So as the angle of attack increases, the lift initially increases, but then eventually the angle of attack reaches that critical point where the airflow separates and the wing stalls. So here, the blue is the angle of attack. We are increasing it. And the red here is the airspeed, which will remain constant. So as we keep increasing the angle of attack, we get different signal energies. And initially it is within the safety envelope, meaning that we know it is in a no-stall condition. But as the angle of attack reaches that critical point, we're going to notice that the signal energies we get start getting outside the safety envelope. And essentially our monitor says, oh, this is not in the safety envelope anymore. I don't know if I'm in a stall or in a no-stall anymore, either because of low confidence or because of unpredictability. And eventually at some point, once the angle of attack is too large, then it is both, again, C predictable and tau confident, where we have a classification of stall, and we can say for sure it is a stall. So again, this is tackling the problem of understanding whether the plane is in a stall or no stall from data coming from the sensor network in the skin of the air. So as a summary, C predictability and tau confidence are key properties for data-driven models. And we can formally prove properties and generate runtime monitors or sentinels to check that, that the system is or is not in the safety envelope. And we can, of course, use different parameters to shrink or enlarge those safety envelopes, getting weaker or stronger properties. We can also use the notion of safety envelopes to create new models. Maybe we didn't test enough angles of attack. Maybe we didn't test enough airflows. So essentially, there are many different ways we can use this idea. Is the data set complete for what we want? Do we want to add more sensors? Maybe we don't have enough sensors. Maybe we need more sensors to be able to have the guarantees that we want. But the idea is here we have a quantifiable value with a formal theory behind, rather than just heuristics and guts, something that can tell us whether things are good or not. Progress envelope is the analogous of safety, where we say, how can we guarantee that the planes will actually reach consensus? And what we do is essentially we monitor latencies, we monitor how long it takes to communicate, and then we use those lower level probability distributions to get a higher level probability property. So, for example, if the one-way latency follows a normal distribution, then you can say the round trip is going to follow also a normal distribution because of Kramer decomposition theorem, where you sum two normal distributions and you get another normal distribution. So essentially, you can use statistical theory to prove probabilistic properties of the application level from the lower level measured values. So that's essentially what it is. I'm not going to get into too many details. There are papers. Saswata Paul finished his PhD thesis with this work. So his thesis is there, very nice thesis, highly recommended. Take a look at it. And he looked at different relay protocols. So there is this multi-copy to-hop relay, where in order to transmit a message, you have to go through one other agent because of your range not being sufficiently high. And then he also looked at queues to model waiting time, where you may have multiple messages and it may take a while to process those messages. So he essentially used informed network theory to come up with the right statistical properties about the system. And all of this, again, is formally proven using Athena. So a lot of work to be done. We have just done a little bit, but there's a lot to be done. Different types of distributions, different types of networking protocols, different types of distributed algorithms. So lots of things to be done, but this is kind of showing a way forward in terms of bringing formal verification to data-driven systems. So I'm going to skip. Again, we advocate for a modular approach. We have general mathematics theory, we may have probability theory, we may have some network theory, we may have distributed algorithms. And the idea is we reuse these modules. Just like we reuse programming libraries, we reuse all these reasoning libraries in different contexts to get the theorems. Runtime verification, where we essentially update, we refine the proofs as our sentinels give us some real-time data, and now we know that the latency doesn't really follow this distribution, but this other distribution. Then we either refine the proof and give a new property, or we say the system is not following the assumptions. Formal properties no longer hold. And these are examples, but I'm going to skip in the interest of time. And get to questions because it's time. Sorry about taking So it's a book I wrote in the first sabbatical, Programming Distributed Computing Systems, a foundational approach I recommend. And I'm working on another book for formal verification of distributed software that hopefully will be coming out in the next few years. So if people are interested, feel free to contact me. I can send a few chapters, and if you're interested in the work, I can share it before it gets published. And thanks to the Air Force Office of Scientific Research, in particular the DDDAS program by Dr. Eric Blash and Dr. Federica Arema as program managers, and the National Science Foundation for a lot of the funding for this research over the years.
Nice. Any questions?
Yes.
First of all, fascinating work. Thanks so much for the presentation. I do have two serious questions, but first, I wanted to save my curiosity. Did you become a pilot because you were working in aviation, or the other way around?
So aviation has been a hobby, and I did not want to work in anything related to aviation because I was afraid I would screw up my hobby.
Then you started to see some problems.
But the turning point was the Air France 447 accident. When I saw the accident from the plane going from Rio to Paris, and it was a turning point because I was once flying in instrument conditions from Albany to Washington, D.C., and actually my airspeed started to decrease. And when your airspeed starts to decrease, as a pilot, my reaction was I have to push the nose down. I don't want to stall. But that didn't feel right. I looked at the vertical speed. Vertical speed was 0. Altitude constant. RPM constant. It was the pitot tube icing. Also. And this small Cessna has pitot heat. So I applied pitot heat. It hits the tube, and my airspeed came back. And I said, you know, why cannot this billion-dollar plane do that? No, seriously, I mean, this makes no sense. So that was the turning point. I said, I'm going to start working on software and systems and verification to make flight safer as much as I can. So good news is I still enjoy flying. It's still a hobby. I love it. We've done a lot of flights. My wife is here. We've gone all the way to California with the girls from New York, like 6 legs. We do a lot of flying, and it informs a lot of the research. So I'm always thinking when I see an accident, how can we prevent such an accident in the future? How could we do things better? And that's been so yeah, it's actually been synergetic, and I enjoy working on this, and I also still enjoy flying.
The more serious questions is, I know that modern aircraft are basically really automated, some of the most automated, commercial vehicles anywhere. But in the case of a very distributed, very complex system like the automated air traffic control system you described, do they have the equipment to sort of react to being given such information?
Yeah, so actually, when I started this work, there was much less communication between aircraft than there is today. Right now, there is a protocol called ADS-B, where planes actually are continuously broadcasting their type of aircraft.
Imagine that.
And as a pilot, I actually get an application on an iPad where I can actually see all the traffic nearby. When I went all the way to California and I was flying near Fullerton, very busy airspace in California, and the controller would come back to us and say, you have traffic at 10 o'clock, at 1 o'clock, at 2 o'clock, at 4 o'clock. Where is all this traffic? It was unnerving. Today with the iPad, you see all the traffic in your screen, and it really makes a huge difference. So yes, it's improving. The communication between planes is getting farther and farther, but at the same time, there is a lot to be done. And of course, the challenge with these systems is you have to prove them safe, you have to certify them, and it makes it much harder to get them, to use the latest things. Now, the Boeing 737 MAX 8 is an example, however, of things going really badly, right? Like how can this MCAS system depend on only 2 sensors? Actually, it depended on only 1. Depending on which pilot was flying, you take the input from the right sensor or from the left sensor. Really crazy. So how can they do that, and how can it be certified? So so unfortunately, there is still a lot to really be done in this direction. I believe that creating proofs is much harder than checking them, so that's why automated theorem provers can take forever to find a proof, and maybe they fail many times. But once you have a proof, checking it is very fast. I believe that a similar approach could be taken for certification authorities, where the burden is on Boeing and Embraer and Airbus and all the airplane manufacturers to create a formal proof that the system is correct, and then the FAA or whatever certification agency should just check it. But we're far from there. We're far from really having formal verification all the way to where it should be.
Still very, very fascinating.
You explained that the safety envelopes in terms of the wing to the sensors.
Mm-hmm.
How can you relate this to the air traffic control scenario? I mean, can you define an envelope for the whole set of airplanes, or is it for each plane individually, and then you check if it's going outside the envelope? So
yeah, I could imagine, for example, a safety envelope for determining what communication characteristics are proper or not to join some airspace. So say you have some radio communication that has a very small range, or it doesn't have the expected performance. You could right away, when there's a candidate with such characteristics, say, you know what, you're going to put everyone here in jeopardy, so not accepted because you're not within this safety envelope. That guarantees that consensus will be reached in under some time with some very high probability, for example. So you could bring this notion of safety envelopes to the distributed system as well. But of course, you need to define.
Because I was thinking that at least in the air traffic control scenario, you assume that the routes are fixed.
That the flight. Absolutely.
Some pilot goes mad and decides to. So how can you use verification or online verification? I don't know.
No.
Just to call the pilot and say, what are you doing?
No, you're absolutely right. In the case of an emergency, so if your engine fails, so you had the plan to go A, B, C, but in the route to A, your engine quit.
Exactly.
So that happens. So what we advocate for here is being able to communicate that. Now, what happens today? What happens today is that what happened in the Hudson River case. The pilot talks to the air traffic controllers. The air traffic controllers create a plan with very limited understanding of what's going on, tell other aircraft to move away, and leave space for this plane. Now, all this can be automated. All this can be done with planes talking directly to each other in a way that is much faster. Sullenberger took 3 decisions in that flight: a right decision, a wrong decision, and a right decision. The first decision he took was, I'm going back to LaGuardia. If you listen to the transcript, as soon as the birds hit the engines, he said, I lost thrust, I'm going back to LaGuardia. And he started a left turn to LaGuardia. That was the right decision. The controller freaked out, when the controller learned about the engine failures, and told Sullenberger, go in the direction 220. 220 is like southwest. The controller is putting the plane in a downwind to come back and land in runway 4. That might be okay if only a single engine had failed, but both engines failed. Both engines failed. So he really didn't have the luxury of going all the way to do a downwind and come back to runway 4. Wrong decision by Sullenberger was to follow the controller's direction. It's an understandable wrong decision because pilots, we are trained to, no, but the first rule in the FAR, the federal regulations for air traffic, it's a huge book that you have to understand. But the first rule says, in the case of an emergency where the safety of the flight is compromised, you can deviate from any of the following rules. He had declared an emergency. So what he had to do was to continue to go back to LaGuardia. He followed the direction of going to 2-0. 45 seconds later, that seems like not too long, you know, very efficient air traffic controllers, very professional people, still really bad. Because after 29 seconds, I think we have a paper where we looked at the trajectory that could have been taken at different points in that flight. It was not possible to go back to LaGuardia anymore. So when the controller told Sullenberger, yes, come back, land in any runway, Sullenberger said, unable, landing in the river. And that was a good decision again, because if he had tried to come back to LaGuardia, he would have crashed. So good decision, bad decision, good decision. But the point is, if you have an Internet of Planes kind of setting, an aircraft in an emergency can detect zero thrust, can forward the, create a plan. We create a plan in under 50 milliseconds for a trajectory to the runway. Can forward that plan to the air traffic controllers, to their aircraft with an emergency sign, and they can move out of the way. They have to adapt. Formal proofs at that point would go out of the window, in some of these cases, unless, at that point, this is one of the cases where you essentially no longer have the assumptions, you no longer have the original route.
In some sense also because in the consensus, you give the right to everyone to vote. And in emergency, one is the leader, the rest just go away, go away of the way.
Yeah. And these things break. If all planes go into an emergency at the same time, it's like same as a distributed algorithm where all nodes fail. And there is some bound but you can still get some behavior, but at some point things break. But still, you can reason about that one single emergency case and try to have some proofs about that. So
in that direction, what is your perspective for the future in the use of AI, machine learning?
Yeah, so AI and machine learning is kind of scary when it comes to airspace and safety critical systems. Because it's one thing to say Toronto is a US city. That's not good, but nobody dies, right? Another thing is to give a wrong direction that can kill people. So AI and ML are going to happen, whether we like it or not. and they're going to be increasingly in our aerospace systems as well. So the question is, what can we do about it? And I think a lot of the techniques that we are moving forward in terms of creating safety envelopes or correctness envelopes and having formal proofs associated to those envelopes, even probabilistic in nature, I think it's better than nothing. So I think what we're doing applies to many of these data-driven models, but we're going to have to live with probabilistic properties. We're not going to be able to formally prove deterministic behavior. Yeah, but it is happening. For example, the Air Force has a controller for a spacecraft and also for an aircraft that was built using reinforcement learning, and it is a neural network. So it's a neural network controller. It was trained with data, and it takes an airplane. There is a leader airplane and a follower airplane, and essentially the control system is supposed to keep some distance that is small but not crash. In the case of the airplane, and in the case of the spacecraft, the safety criteria is that the closer the distance between the deputy and the main spacecraft, the smaller the relative speed. So essentially, the spacecraft has to slow down as it docks. And these systems work. You know, I mean, my first question is, does this thing work? Yes, it does. It works, but prove it correct. It's very hard.
That's possible.
No, it's not impossible. We have some ideas,
Really?
but it is limited. So you have to essentially bound it, as long as the initial position is within some bounds. I mean, you can, for example, say if it is this specific initial position and this specific initial relative velocity, it works. But that's not good enough, you know. I mean, so the question is, how do you bound those? At Stanford, they have quite a bit of work, if you're interested in that, where they essentially try to formally verify neural networks. And the approach is essentially to, again, bound the input space and try to find those regions where you can still guarantee some property of the input-output function. But it is not complete. So it essentially says, it puts strong restrictions on the input space function. But it's still useful. So it's a brave word. But I think formal methods help. Even if it's sufficient, it's better than nothing.
Nice. Thank you.
Thank you very much.